Hi everybody, in this video I'm going to go over how to make an energy bar chart and an equation based on that when given a situation involving an energy change. So in order to do this, we really need to know our different types of energy. So I'm just going to take a second and explain them here on the side. So K is our kinetic energy. This is our energy due to the motion of an object. So whenever an object is moving, it has kinetic energy. UG is our gravitational potential energy. Okay, and this is the energy due to an object's position in a gravitational field. So whenever you have a height change, like an object moves up or down, then it has a change in gravitational potential energy. It's really important for us to set a zero reference point for our system. And then anything that is above that point has gravitational potential energy. And you can set that zero to wherever you want. We're going to go into this in a second. US is our elastic potential energy. And this is the type of energy that is stored in an elastic object. So if you have something like a rubber band or a spring that is stretched or compressed, that object has elastic potential energy when it is stretched or compressed. When it's at its equilibrium state, like just chilling, not being stretched or pressed, then it doesn't have elastic potential energy, okay? And we have this UINT. This is internal energy. This is energy due to the motion of the particles in an object. So whenever you have something that warms up or it gets compressed or it is hit, right? Any sort of changes in its composition or if it warms up or cools down, that would be a change in internal energy. And lastly, we have work. And work is a change in energy, and it's caused by a force that is external to your system. So if you have something outside of your system that exerts a force on it, there's going to be work done on your system. And now that work can be positive and increase your energy of your system, or it could be negative and decrease it. Now that we know our types of energy, let's look at this first situation. So we have a skateboarder moving quickly, slides up to the top of a ramp and stops. So I'm going to say my system here, I'm going to include my skateboarder. Ooh, let's spell that correctly. The skateboard that they're on. Let's include the ramp and the earth. Notice I always include earth in my system because in order for an object to have gravitational potential energy, you need earth to be included in your system. And then I just included everything else that was mentioned in this situation. So now I'm going to sketch. So here's my ramp. And first, my skateboarder is moving quickly, but they're at the bottom. Okay. And then after, they're at the top and they're not moving. Okay. Let's also put our 0 point at that lowest space, so right here. Okay. Now let's start looking at what kinds of energy we have. So starting initially, it says it's moving quickly on the bottom of the ramp. So does it have kinetic energy? Well, it's moving quickly, so yes, it should have some kinetic energy. So I'm going to put a bar here for kinetic energy. Doesn't really matter how high you make it. I made it 2 bars. Does it have gravitational? Well, we set our 0 point as that lowest point. Initially, it's at that lowest point, so we have no gravitational. I'm putting a 0 here. Does it have elastic potential energy? Well, that would have to have some sort of elastic object like a rubber band or a spring, and we don't have anything like that here, so I'm going to put a 0 for that. I'm going to skip work for a second. Let's go back to the after. All right, now we're looking at our after situation, and it says it's at the top of the ramp and stops. So if it stops, that means it's not moving. If an object is not moving, it does not have kinetic energy. So I'm going to put a 0 here for kinetic. Does it have gravitational? Well, it's above our 0 point, right? So that means it must have gravitational. Okay, I'm going to put a bar there. Does it have elastic? Again, there's no sorts of springs or rubber bands, nothing stretching. So I'm going to put a 0 there. And then I'm looking at internal energy. And it doesn't mention anything sort of has friction against it, it doesn't warm up, it doesn't get compressed. So I'm going to say no. Okay? So initially we have kinetic energy, and finally we have gravitational. Now I want to take a second and think about work. Is there any object that is pushing our skater outside of the system? So we just have the skateboarder, the skateboard, and the ramp. So there's no other force exerted here, and so there's not going to be any work. And that makes sense because we don't really have a change in energy here. We have a transformation from kinetic to gravitational, but no energy is lost or gained. So it makes sense that we have no work. Now we can make an equation based on this. And how I make an equation is if there is a bar, I rate the symbol for that type of energy. And if there isn't, I just keep it as a 0. So I have K plus 0 gravitational plus 0 elastic plus 0 work equals 0 kinetic plus we do have gravitational plus 0 elastic plus 0 internal. Now I'm just going to rewrite this, getting rid of all of my zeros. And I have K equals UG. That's my final answer. So we notice here, first I just wrote down what my system is by including the Earth and anything that was mentioned in my situation. Then I drew my sketch for before and after and labeled a 0 point for gravitational potential energy. And then I went through each type of energy and figured out if there was any of that type of energy before or after, and made my bar chart based on that. Then I used this to come up with an equation based on my bar chart. Now in the future, we're going to have numbers that we're then going to use that equation to plug in numbers and solve. But for now, we're just writing these equations qualitatively. Let's take a look at a second scenario. We have a soccer ball is moving quickly across the ground, and then a player stops it with their foot. So my system, I'm going to include the soccer ball, and I'm going to include the ground, and I always include the Earth. Okay? I'm not including the player with their foot, and I'm going to explain that in a second why I did that. So now let's sketch our situation, and before our soccer ball is moving quickly across the ground, and then after the soccer ball is not moving. Notice this doesn't say anything about hills or it moving up or down, so I just kept it at that same level. Since it's always at that same level, let's just make that our 0 reference point. Okay. Now we're going to look at our types of energy. So initially, we have the ball is moving quickly across the ground. So if it's moving quickly, then we must have kinetic. So I'm going to draw a bar for kinetic. Now, does it have gravitational? Again, it doesn't say anything about hills, doesn't move up or down. And I made my 0 reference point as just that same lowest point. So I'm going to say no, there's no gravitational. Is there elastic? Well, elastic would need some sort of spring or rubber band. We don't have anything like that. So I'm going to say 0. I'm skipping work for now. Okay, then after, it stops with their foot, right? So stops, that means that it's no longer moving. If our object isn't moving, it has 0 kinetic. Now, it has at that same reference level, so it still doesn't have gravitational potential energy. We don't have any springs, no rubber bands, nothing like that still, so no elastic. Okay? Now, thinking about this, we know there's going to have to be something like work or internal energy. We didn't notice that this warms up, right? And also, we did not include the player in our system, but the player exerts a force on that ball, okay, external to our system that makes it stop moving. So if we have an external force on our system, that means we have work. So there's going to be some work in the system. But we have to figure out, is this going to be positive or negative? Well, it stops it, right? So it's moving and then it's not moving. That means it had kinetic energy, then it didn't have kinetic energy. So the energy decreases. Also, the ball was moving this way in the positive direction, and the person was exerting a force in the negative direction. So both of these things mean that we have negative work to our system. So I'm going to draw a negative bar for this, like that. And then I'm going to say it has no internal energy because there was nothing about warming up or cooling down. It did stop, but it wasn't due to a frictional force. It was due to that foot, which is external to the system. Okay? If we had just had the rolling ball come to a stop because of the friction, if we included the ground in our system, then we would have an internal energy. But it was a person that stops it, and that person is external of our system. That means they're exerting a force from outside the system, so there is work done. Since it's in the opposite direction of motion, and it decreases the energy of our system, that work is negative. Notice here I drew 2 bars for kinetic, and I drew a negative 2 bars for work, just to make sure that it was even. Now let's write our equation. So we have kinetic, right? There is a bar there, plus 0 for gravitational, 0 for elastic. For work, we do have work, but it is negative, so I'm going to put minus work. Okay, it's negative, so I'm putting minus. Equals 0 for kinetic, plus 0 gravitational, 0 elastic, and 0 internal. Now let's just simplify, get rid of our zeros. We have kinetic minus work equals, and everything on the right is 0, so I'm just going to put 1 0. And that's my overall equation. Let's look at a third situation. Here we have an elastic popper toy. I don't know if you've ever played with those. You turn them inside out and they pop up. Is turned inside out and placed at rest on a table. After, the popper shoots up and is moving quickly. So let's make our system the popper, the earth, and the table. So at first we have our popper is inside out on the table. And after, it's right side out and it's moving quickly. Let's make our starting position, this lowest point, our 0. All right, now we're going to look at our bar chart. So initially, it is placed on the table, so it's not moving. So I'm going to say we have 0 kinetic. It's at our 0 reference level, our lowest point in this scenario, so I have 0 gravitational. Now, it does say this is an elastic popper. Okay, if it's an elastic toy, it's turned inside out. So we did something to this to add elastic potential energy. So there is, in fact, elastic potential energy in this case. Okay, now let's look at our final state. In our final state, it shoots up and is moving quickly. Since it's moving quickly, we know it has some kinetic energy. And it shoots up. It's above this reference level. So it must have some gravitational potential energy as well. At this point, it is no longer turned inside out. So it's not stretched or compressed anymore. And that means it no longer has that elastic potential energy. Just like if you stretched out a rubber band and then you let it go, after you let it go, it doesn't have that elastic potential energy anymore, only when it's being stretched or compressed. So our initial state does have elastic potential energy, but our final does not. I'm also going to say there's no internal energy because there's no warming up or, being crushed. And we notice in this case, there is no external force to the system. It's already turned inside out, and then it just turns itself right side out and pops out. The only things included are the popper, the earth, and the table. None of those exert forces on our system, and our energy doesn't change. So we have no work in this case. Notice here that I made the elastic potential energy initial 2 bars high, and then I made kinetic and gravitational each 1 bar high. Okay? I want these to make sure that they add up. It doesn't matter if you made it 4 and then 2 and 2, or 4 and 3 and 1. That would be okay with me. I just want you to make sure that they add up here. Now let's write our equation. So we have 0 for kinetic, 0 for gravitational. We do have elastic. 0 for work equals, we do have kinetic, we do have gravitational, we don't have elastic, so 0, and 0 for internal. Now let's rewrite this without all of our zeros, and we get US equals K plus UG. Okay. Last situation here. Here we have an ice skater starts from rest at the top of an icy hill. When she reaches the bottom, she is moving quickly and her skates have warmed up. As I read this, I just sort of underlined the key terms here that I think are going to help me. So let's include our ice skater in our system, her skates, the hill, and the earth. We always like to include the earth. Let's make our sketch. So she starts at the top of our hill from rest, so she's not moving. Okay. And when she reaches the bottom, she is moving quickly. Okay, and her skates have warmed up. We have to make our 0 point, so we're gonna make it the lowest point. So that's this point here. All right, let's take a look at our bar chart. Okay, so initially she starts from rest. That means she's not moving, so she has 0 kinetic energy. But she's at the top of an icy hill. We set our 0 here at the bottom. So the top is going to have gravitational potential energy. Okay, let's make that like this. I'm gonna make it 4 high. You can make it however high you want. Does it have elastic potential energy? Well, here we have no elastic objects, no springs, no rubber bands. So I'm gonna put a 0 there. Looking at our final state, it says she is moving quickly. If she's moving, that means she has kinetic energy. So I'm going to draw a bar for kinetic. Does it have gravitational? Well, now she's at her lowest point. So at this point, she has no gravitational. So I'm putting a 0 for that. Elastic, still no stretchy objects, nothing stretching or compressing. So putting a 0 for elastic. And it says her skates have warmed up. And that warmed up is a key here that says there is some internal energy change. So I'm gonna put a little bar there for that. Now thinking about work, is there any object external to the system that does work on this? Well, the skater goes down because of the force of the earth. It has that force that the hill exerts, but that's already in our system. So no, there's nothing external to our system exerting a force on it. So in this case, we have no work. Now, if you did not include the hill, okay, if instead you said, okay, there's no hill, then what you would have is that you wouldn't have internal energy, but you'd have work, okay? So then the hill would be the thing that made it warm up, so you would have negative work. But in this case, we're gonna include our surface and then have internal energy. This is sort of like a good rule of thumb. If you include your surface and it warms up or slows down, there's some sort of frictional force. If you include the surface in your system, then you're gonna have a change in internal energy. But if you don't include it in your system, then you're gonna have negative work. In this case, I included it in my system, and since it warms up, it's gonna have internal energy. So here's my bar chart, and notice again that I made the kinetic and internal each 2 bars, and then that adds up to my 4 bars for gravitational. And again, it could just be 4, 3 and 1, 2, 1 and 1, but you want them to add up the total before to equal the total after. Last step here, let's write our equation. We have 0 kinetic. We do have gravitational, so I'm writing UG. 0 for elastic, 0 for work, equals K for kinetic, we do have kinetic, 0 gravitational, 0 elastic, and we do have delta U INT for internal. Okay, let's just take one last step, get rid of my zeros, and I have UG equals K plus delta U INT. That's my final answer. So in this video, I went over how to look at a scenario, figure out what kind of energy it has initially and finally, track that using a bar chart, and then make an equation based on that. Hopefully this was helpful.